Yeah, okay. Okay, just wait a minute. So can you hear me?
Yes.
Okay, so I will start my presentation. Good morning. My name is Yankan Song. I'm from Tsinghua Sichuan Energy Internet Research Institute, and I will use a few pages to introduce our work on high-performance power system simulation based on heterogeneous cloud computing. So first, I will introduce the background. So our research team is devoted to providing high-performance power system simulation solutions using advanced algorithm, uh, cloud computing, and heterogeneous parallel computing technologies for many years. There are two reasons for why we do this work. First, the power system, the power grid is growing larger and complicated these years. In order to simulate and analyze it efficiently, we need more computational resources. Second, the computing devices are developing and evolving very fast in the last 2 decades, from CPU, a traditional CPU to ARM CPU, GPU, and IPG and ASIC. So more heterogeneous frames, computing frames are proposed and used in a generalized computing area. So traditional power system simulation solvers should be reformed to adapt to these new frames to meet the increasing simulation burden. And there are many kinds of heterogeneous computing frame. A static software or program cannot perform well on all these devices. To overcome this problem, we develop a cloud-based power system simulator based on different heterogeneous devices. We name it CloudPSS. It is a SaaS-based software for power system EMT simulation, power flow studies, and other kind of simulations. So users only need to use the web browser without having to configuring complicated drivers, install softwares or compilers, and other hardware environments. So it is available on our website, cloudpss.net. The CloudPSS platform incorporates a heterogeneous cloud service integration framework. It has three parts: a user interface in the web browser, a data exchange platform, and the heterogeneous computing grid. The web-based workspace is a visualized modeling and result analysis tool. So we can build models by dragging, dropping, and connecting components, just as other software does. So after the model is complete, the users can set up simulation tasks and configure simulation parameters and receive and analyze results in the data visualization workspace. The data exchange platform is the middleware of the CloudPSS. It generates the virtual simulation engines for each simulation task. The virtual simulation engine I will introduce later. So it launches the task onto the cloud and to store the return results. On CloudPSS, each simulation task will be packaged as a virtual simulation engine, or VSE here. The VSE is based on a Docker. It is a kind of virtualization tool. So when a simulation task is received by the VSE, the platform first selects a basic Docker image as the VSE template, and it contains corresponding operating system, hardware drivers, and other dependencies. Then the model and the task definitions are sent back to the automatic code generator to generate the simulation program and compiles it into binary files. Finally, all these files are packaged together as a VSE Docker image and then sent back to the heterogeneous computing grid to proceed the simulation. So there are 5 steps to finish the computation in the CloudPSS platform. So in order to be compatible with different computing devices and to get higher efficiency, each program needs to be reorganized and compiled at runtime. This figure shows the workflow to generate the simulation program. So first, we should build the physical model in the CloudPSS. The original physical model definitions are translated into a computation graph model. Here we call it CGM. And then the computations inside the CGMs are rearranged and the computation resources are finally mapped onto the CGM. So finally, the code to proceed the CGM is automatically assembled and compiled for corresponding devices. And up till now, the code generator supports CPU, NVIDIA GPU, Sunway CPU. Sunway CPU is a basic chip in supercomputer Sunway Tap-Lite in China, and we recently have tested on the ARM-based CPU, such as Apple M1 chip. It even works more efficient than traditional x86 CPU. So it shows potential of the future ARM-based CPUs for in generalized computing. Here is an example of the proposed automatic generated EMT solver. The solver can be divided into 3 kernels. One kernel to calculate the control system, and one kernel to calculate the electrical system, and the other is to solve the total nodal voltage equation. So this is the basic process for the EMT, the electromagnetic transient solver. And we also build 2 kind of solvers. One is a generalized solver. It is it can automatically compile on different platforms using either ICMD or SMT parallel pattern. So on CPU we use multi-core and SMD strategy to accelerate large system simulation. And on GPU, we use the ICMT or single instruction multi-thread pattern to accelerate fine-grained parallel computations. So this is the basic process on the in generalized parallel way to accelerate the EMT simulation. So another solver we use just-in-time compiling technique. So it first interpreted the system model and then generate and compile the simulation codes for each unique power system. So the codes generated by the automatic code generator is we use this kind of kernel because this kind of kernel can maximize the simulation efficiency. So because of time limit, I won't go into details here. So let's just say several benchmark performance. First is CPU-based EMT simulation. For several regional grid size from 1,000 to 10,000 buses, the CloudPSS can finish a 1-second simulation in less than 30 seconds. For multi-core solver, the CloudPSS can finish same work in less than 5 seconds using 32 cores for a system with 1,000 and 500 buses. So this is just the CPU performance. We only use multi-core CPU to accelerate it. And here is the GPU performance. We made 3 tests. Test 1 is a scalability test for a system with more than 16,000 buses and nearly 1,000 photovoltaic subsystems. The GPU gains 16 times speed up over CPU. Test 2 is a multi-scenarios test. We build over 1,000 scenarios for such system and benefit from vectorized computing on GPU. It gains 80 times speed ups than on CPU. And the final test is a practical utilization. So we based on the batched solver on the GPU, we develop a power system frequency sweep analyzer on CloudPSS. If we sweep 1,000 scenarios one by one for such kind of system on PS card, a typical time cost is 18 hours. So, however, if we use GPU, it only takes less than 3 minutes, totally nearly 400 times speed up. And we already, so up to now, we have already let CloudPSS become a public resource, a public research tool, free to all on our website. And now we released on the website we released 3 one-core solver, only based on CPU, yeah, including power flow solver and EMT solver and a shifted frequency based EMT solver. So the shifted frequency EMT solver, it is a kind of dynamic phasor based solver. For the large-scale power system, it can use larger time steps to simulate large-scale system more efficiently. And all the researchers can register a model and perform the simulation on this website. We also released the CloudPSS SDK for researchers to call a native solver by the API to do further studies. So now the SDK and API can be installed through the Pipe libraries. And we have released a CPU-based, we have supported a CPU-based EMT solver and CPU-based power flow solver and CPU-based SF EMT solver. So they can all be called or be performed by the SDK. So anyone can log into the website and obtain the SDK token and the documents for this for the CloudPSS SDK. So and finally, in addition, we do a little further this month. We have developed a GPU-based multi-scenario frequency sweeping application, which uses kernel and the SDK and a tool, which I just mentioned. The kernel is based. The kernel is deployed as a backend of the web-based application to obtain the harmonic impedance in real time. For example, here is the real-time analysis of a wind turbine. We need a CloudPSS simulator, and we should integrate measurements or sensors and transfer the measured data, which is the operation status of the real-world wind turbine, back to the simulator. And then we should initialize the simulation model to its real-world operation state and perform the initialization and perform the frequency scan using massive simulation tasks on GPU. And this demo or the preview is also released on CloudPSS. Here is the website. I should emphasize it that why we do this work, because we found that in China and in other places that in large-scale AC/DC systems, when the renewable energy or wind turbine and solar farms are integrated into power system, they may cause some phenomena such as the subsynchronous oscillation. So in order to find which frequency is dangerous in the real world operation, we need some tools based on the simulation like this. So we do this work. We build this application, and maybe it can be used in the real world power system operation and dispatching. So finally, I will give a little conclusion. We are continuously adding new functions to the CloudPSS platform, and we want to improve the simulation performance in the future work. And in our next step work, we will continue to extend the CloudPSS API and SDK to support more languages such as maybe C, JavaScript, and Julia. We found that these several languages can extend the CloudPSS SDK abilities to support such as the research work and other real application work. In addition, we are still working on adapting to other devices such as the Xilinx FPG and the Zinc. And I'm looking forward to share more progress in the future meeting. Thank you for listening. So.
Okay, well, great. Thank you so much for that presentation, Dr. Song. I think it was very interesting, and I'm really pleased to hear that CloudPSS is available open source. It's great that other researchers can also try it. I'll request the attendees to please post their questions on the chat box, or if you have a question, so you can unmute yourself and ask the question as well.
Okay.
I have a couple of questions, Dr. Song. So the first one is the EMT solver that you are using. Is this something that you have developed, or is it a commercial solver?
The EMT solver in this platform is a self-developed solver.
Okay.
It is a similar algorithm such as the EMTP type program.
Okay.
But it is totally self-made. Yeah.
Okay. Okay. And my second question is, you mentioned about using GPUs and CPUs as well. So I was wondering what part of your computation or calculation is done on the GPU and what part is done on the CPU.
Yeah. I should emphasize it. Yeah. We turn back to this page. So we built several solvers because the solver is based on automatic generated kernel and generalized kernel. So for the generalized kernel, we just get two ways, two accelerating ways. The first kernel, the first solver is totally on CPU. So we only use the multi-core solver, multi-core parallel characteristics of the CPU on this platform. And the second solver, we put all the computations into the GPU because we found that during the EMT simulations, we need to repeat several integration time steps for each computations. So the computations in each time step is nearly the same. So if we put several computations on CPU and others on GPU, we need lots of data transition from the CPU to GPU, which may cause the data delay or a time delay. So it is not the most efficient way. So we put all the data and put all the simulations all on the GPU. So it's totally a GPU-based solver. And this two kind of solver we can. Yeah, we provide two kind of solvers. For the one is for totally CPU and one is totally for GPU.
Okay. Okay. And then on the GPU, when you're solving the linear system, do you use like a dense solver, or is there some solver that you use from NVIDIA or some other vendor?
Yeah, it's sparse solver. Yeah, sparse solver or cool solver, and we use cool solver or cool sparse, which is provided by NVIDIA.
Great. Thank you. Any other questions for Dr. Song?
Yeah, I should stop the screen sharing to see the notes. Yeah, maybe. I cannot see the questions.
Yeah, so far I'm not seeing any questions over here. So if there are any questions, you can unmute yourself and ask.
Yeah, Dr. Song, this is thanks for the presentation, very good one. Actually, I have a question here on this one on slide 7 that you were saying that you have two kernels, one for controllers, the other for the electric parts.
Yeah.
So do they communicate to each other at each time step, or they are just separate? How do they communicate? For example, you have a controller, it needs to set something for your electric device, and then there should be some. So I mean, they are not very independent from each other. If you agree with that, or
yeah, in traditional power system electron EMT simulation, we can just divide the total computations or total simulation process into 3 parts. The first part is to solve the control system by the next step control system output by the last step value, and then use the control system output value to calculate the historical values of the electromagnetic of the electrical components. So this process is called calculating the electrical components. So the interface between the two kernels, and we use the we use shared memory to store the temporary results to help the two kernels to communicate with each other.
Okay, and is there anything like an iteration between these two kernels, or?
We can introduce the iteration here, but in traditional EMT simulation, such as maybe even the real-time simulation, we want to avoid the iteration in the real applications, but we can introduce it in this solver, because the iteration did not the iteration is also, we can do the iteration by this. We perform one-step simulation, and then we found that it's not convergent at this time, and then we just turn back one step and then recalculate it again, and we can do this work. So for each time simulation, we can still use the proposed EMT solver for the, so on GPU is there is not there's not difference between the iterative ones or non-iterative ones during the simulation process in each time step.
Okay, I'm not sure if I understood it correctly, but that's okay. And I don't know, is there other question, or I can ask? I have more time.
Couple of questions, maybe Dr. Song can address that, and we can get back to you, Wahid.
Yeah, let's continue.
So the first question is, can the public make use of CloudPSS to simulate large-scale systems? If yes, what is the process of requesting for more CPU, GPU cores?
Excuse me, pardon me. I can catch that one.
So you can also see this in the meeting chat. The question basically is, can CloudPSS be used to is available publicly for simulating large-scale systems?
Yeah, the solver itself can simulate a large-scale system, but the public resources, we only we restrict the public resources on the website, because if one person just access the CloudPSS and call it using large scale using maybe many computing resources, and other people maybe can't use it. So we now just released the one core simulation engine for the public users to use. But we, in our internal networks, we can we have many other kind of solvers which can use which can use up to 64 core solver to calculate large scale power system. That if you have some, if you want to use it, you can contact me, and maybe I can give you some a VPN, and you can access to our internal network and to use the large scale power system solver.
Okay. Yeah. So I think so I think the answer here is that, you know, if you can contact Dr. Yankan Song, he can provide you more information about how to use more resources. The second question is, what is the time step used to simulate the Segre B4 DC network? Also, what is MC model used in that simulation?
1 microseconds to 50 microseconds. We can if the time step is larger, maybe the accuracy will decrease.
Okay. And then what is the MMC model used in that simulation?
The MMC model is how to say it? Maybe it is a kind of 7 equivalent model.
Okay. Okay. Wahid, if you have more questions.
Sorry, I just stopped the slide sharing because I cannot see the notes
Okay.
when sharing the screen. Yeah.
Lucia, I have a question, but I guess maybe let's start the second presentation because now we are on time. So there is time at the end. I ask more questions.
Okay, sounds good. So thank you, Dr. Song, once again for this exciting presentation. And we'll move on to our next presenter.
Okay, thank you.
Dr. Kim, are you online and can you share your slides, please?
Yep, sure. Thanks, Jerry.
Okay, so our second presenter is Dr. Kibaek Kim. He's a computational mathematician in the Laboratory for Applied Mathematics, Numerical Software and Statistics in the Mathematics and Computer Science Division at Argonne National Laboratory. And he's a senior scientist at large at University of Chicago Consortium for Advanced Sciences and Engineering. His primary research focus is on optimization modeling and solution for large-scale optimization, in particular stochastic programming and mixed integer programming that is capable of running on high-performance computing systems in applications to complex energy systems and resilient infrastructure systems. Before joining Argonne, Dr. Kim obtained a PhD degree in industrial engineering and management sciences from Northwestern University. He's also a recipient of the DOE Early Career Research Award given to him in 2019. So thank you, Dr. Kim, for joining us, and we are looking forward to your presentation. All yours.
Okay, can you see my screen?
Yeah.
Right. Thanks, Jerry, for the invitation to give the talk at this task force meeting. So I'm going to talk about our recent work and progresses made for the ACOPF solution for solving the ACOPF problem on GPU. This is a part of the effort that we are making for DOE, Department of Energy, Exascale computing project, and other projects too. So my name is Kibaek Kim. I'm a computational mathematician at MCS division at Argonne National Lab. This is a collaborative work with many other colleagues, and I will acknowledge them later in the talk. So exascale computing, what is exascale computing? So so in the US, particularly in the science domain, we've been talking about exascale computing and capability and machines, etc. So exascale computing is actually that the compute machine that can perform exaflop, at least one exaflop. Exaflop is 10 to the power of 18th floating point operations per second. So to me, I'm not a computer science, so that is not really, that doesn't mean much to me. So what you can think of is that the one exaflop is similar to the operation one human brain can do. So that you can give you some idea. So this for achieving the capability, the full use of exascale computing capability, we need to make sure that we can actually make full use of GPU, because the future computing machines like exascale computing architectures are the clusters of many GPUs and CPUs. So in this talk, I'm going to target the solution of ACOPF problems that can be solved on GPU or multiple GPUs. As many of you already know, the ACOPF problem is a nonlinear non-convex problem to minimize this cost function F over the power flow equations and the electric grid topologies, and also the physics bounds on real power, reactive power, and voltages. So for example, in our experiment results given later in the talk, we're going to solve 70,000 bus system on GPU. This problem can actually have up to more than 150K variables and more than 270,000 constraints with more than 2 million non-zero components of the system. So it's a really large scale of nonlinear optimization. So let me briefly give you some nonlinear programming 101. So we actually consider the following formulation for the generic nonlinear programming optimization. So we minimize objective function f of x. X is the decision variables here in dimension n, and the constraints are given as a c of x as a function, which can be nonlinear equations. And then we can safely assume that the constraints are equality, and then we have the bound constraints on variable x. So this is a generic form. So the common approach to solve this problem is to pose a KKT condition, Kurasi-Kunta conditions, to make sure that our solution is satisfied by this condition. Once the solution is satisfied this condition, then we call it optimal, actually local optimal. So finding global optimal solution is NP hard, difficult. So usually we are happy with a local optimal solution from the problem. So whenever you solve nonlinear optimization problem or ACOPF by using state-of-the-art or the off-the-shelf optimization solver, you usually find local optimal solution, not global. So the common algorithm or widely used algorithm for solving this nonlinear optimization problem is interior point method. Interior point method is nothing but iteratively running Newton's method as we increase the mu parameters here in the KKT system. So this is a very generic scheme. So the reason I'm giving you this idea or the background of the nonlinear optimization and nonlinear optimization algorithm is that, so it ended up solving like this simple, or not actually simple, AX equals to B, the system of equation like several times to find the solution. So here the AX equals to B, and A is a large scale matrix, which can be indefinite and very large. And usually in ACOPF, this matrix A is very, very sparse. So the rest of this slide is not really useful. So the idea is that how we can solve this AX equals to B efficiently on GPU if you want to use GPU. So accelerating this AX equals to B. So usually the techniques used in the for solving AX equals B is to LDL factorization. So to do so, there are some papers that exploited the GPU capability for solving these equations, AX equals to B, and benchmarking results here. So there are like many well-known high-performance linear algebra solvers. They were very well performed on CPUs, and there are a few GPU solvers. And as you can see, that GPUs are relatively slower than CPUs. So in some cases, so particularly for the ACOPF problem, when we solve AX equals to B, GPU solver is actually close to the virtual world benchmark. So this is one observation, and this is another recent experiment. actually performed by our project team. So for solving actually ACOPF and benchmark the linear solvers, again, our conclusion or my observation is that linear solvers are not yet ready for fully utilizing GPUs. So here's our approach. So the choice of our approach is to take the algorithmic decomposition as composed to the linear algebra decomposition. So what has been done in the past for utilizing HPC and many CPUs is that linear algebra decomposition at the linear algebra level to use multiple CPUs and threads. But here we use the algorithmic decomposition to the problems. So the basic idea is that many of you may already know, or here ADMM approach if you were somewhere in optimization area community. So the idea is that we copy some of the variables and then make sure then they are gonna be consensus in the end. And then by relaxing these consensus constraints, we can actually decompose this system of equation into two independent systems or subproblems. So then the idea is that we want to decompose a large-scale optimization problem into many tiny subproblems, many tiny optimization subproblems. So it's called the Lagrangian decomposition. In general, Lagrangian decomposition is a very general name for many specific decomposition algorithm. Actually, we can see that ADMM approach is also based on Lagrangian decomposition. So idea is that as I mentioned before, we impose consensus constraints to make sure that two different subproblems are so the idea is that we want to make a copy of these variables to decompose the system into two pieces for this example. And then we can take the Lagrangian relaxation or augmented Lagrangian form by adding these penalty terms. Then the system becomes the constraint set becomes two independent decoupled set of equations. So this Lagrangian-based decomposition has been successful in large-scale optimization, and then and has been parallelized for the use of HPC. And we also found some interesting results and algorithm development for solving ACOPF problem that based on the decomposition of the system into individual components. So the idea is that we're gonna explain. I believe we're gonna explain the details later. So the idea is that we take the whole electric grid and then decompose this grid into individual pieces. For example, generator, bus, and transmission lines. And then each one of the components consists of a small, tiny optimization problem, sometimes giving us a closed form solution. And then we make sure that we find the solution by adding this consensus constraints on top of the decomposition. So our observation is that the parallel solution time is very small and very competitive and promising. But there are delays by running the when running this distributed optimization algorithm. So if we can accelerate this part, and then if we can improve this part on GPU and exploit this similar structure on GPU, then we should be able to achieve a fully parallelized and scalable algorithm. So again, we're gonna solve this ACOPF, and then actually in specific, we're gonna decompose this entire optimization formulation into pieces. So this is what we are doing. So we are decomposing this whole optimization problems into pieces. Each piece may represent generator or line, transmission lines, denoted by L, or buses. And this individual problem is very, very easy to solve and tiny. For example, this generator subproblem can give us a closed form solution, and the bus subproblem can also give us a closed form solution. And line problem, this is actually a difficult problem again, nonlinear non-convex problem. We still have nonlinear constraint g of x equals to 0, and also bound constraint. So we still need a nonlinear optimization solver that can fully run on GPU. And the dual update is to make sure that we satisfy the consensus constraints. So all we need to do is to take the iterations between generator bus lines of problems and update the dual variables and again until we find the solution. So yes, this is the sort of the overview idea of using GPUs. We are streamlining these tiny subproblems on GPUs for solving like many but tiny subproblems and updating GPUs at the same time. So this is well streamlined on GPUs and batching these tiny nonlinear subproblems. But again, we still need to solve tiny nonlinear subproblem. Actually, this nonlinear subproblem has only 6 variables and 2 equality constraints and 4 bound constraints. So it's very tiny, but still it's a nonlinear non-convex problem, easy to solve. In theory, still NP hard. So what we want to do is to solve this problem fully on GPU without any communication, data transfer between CPU and GPU. Our algorithmic choice for solving this problem is Newton-based trust region method. Actually, this method is called Tron. It was developed like early 2000. It developed in 1999 by our senior scientist Jorge Morhe, and it's actually for solving bound constraint nonlinear optimization. But the targeted problem we are solving here can be formulated by taking the augmented Lagrangian. We can reformulate the problem into bound constraint nonlinear optimization. So we have implemented this Tron algorithm that can be fully running on GPU. So this is some of the details that we made for accelerating the algorithm to design the algorithm, particularly for GPU. We have fine-tuned the algorithm specifically for CUDA here, but the general idea, design choices may be holding for other architectures like AMD and Intel, etc. So all of this work have been done by my colleague Kibaek Kim. So he's the expert. I can only present the results and the design choice, but I would like to acknowledge his effort for designing this algorithm. So here are some numerical results for demonstrating the scalability of Exatron. We are not solving yet the ACOPF problem. So what we are doing is that we are streamlining the best transmission line problem here for 2,000 bus system, 6,000 bus system, 9,000, and up to 19,000 ACOPF test instances. So what we did is that as we increase the number of subproblems, which is called weak scaling, the solution time increases linearly. And also, as we increase the number of GPUs, our problem can be solved on multiple GPUs as well. So the scaling, the solution time is scaling very well, except for one instance. Actually, this white figure should be generated from the ACOPF solution. So to see what happens in these two instances, like 13,000 cases and 9,000 cases, we looked into the details of the numerical results, and we found that there are load imbalancing issues, meaning that as we use more GPUs, we found that a couple of GPUs are working harder than the others. So it's GPUs 2 and 3 are running longer than the others. So this can be resolved by some of the load imbalancing techniques that we have developed before, but it's a work in progress. And this is another numerical comparison to see the speed up of GPUs achieved by GPUs versus CPUs. So our experiments were done on Oak Ridge National Lab Summit. Summit is the fastest supercomputer in the US and the second fastest computer in the world. So we are using 6 GPUs here and 40 CPUs on one node to compare the solution time. And then we see that as we increase the number of problems or the size of the ACOPF problem, we achieve more speed up to 35 times faster than CPU solution time. So far, this is sort of the earlier work that we have done, and so far submitted this result to a journal. And later, we have improved our algorithm based on the existing theoretical work by Sun and Sun, 2021. So the ADMM algorithm is the conventional ADMM algorithm doesn't guarantee the global convergence. But in this two-level approach by Sun and Sun guarantees the global approach, and we have implemented. And then this doesn't actually affect the general structure of our algorithm. And finally, we can benchmark our solution time as compared to IPOP. IPOP is one of the best. I would say it is the best nonlinear optimization solver. And our finding is that our ADMM solver on GPU is consistently way faster than IPOP solution. And also another advantage of using our solution is that we can actually do warm start because of the nature of ADMM algorithm. So if we do warm starting over the period, rolling horizon of multi-period ACOPF problem, then the solution time can be significantly improved compared to the IPOP, although the static single period is already faster than IPOP. And I believe I have like 2 or 3 minutes left. So one of the downside of using ADMM is actually the ADMM is very sensitive to the choice of penalty parameter. So one of the side efforts that we have made during the summer with a summer student from Georgia Tech, we actually try to learn the parameter update scheme by using reinforcement learning problem. This is the details of the reinforcement learning scheme that we have applied for learning parameter update. this is a result. So the MANA paper is the most recent the ADMM paper that is applied for solving ACOPF problem. And as you can see that our reinforcement learning policy can learn the parameter update scheme and thus can accelerate the ADMM algorithm. So for example, like in 118 bus system, it took 486 iterations, but by learning the parameter update scheme, it has been, the number of iterations has been reduced to 335 iterations. And this is not trained, the policy is not trained for a particular load profile. This is for unseen load scenarios. Again, even though the RL policy is not trained for any contingency scenarios, this RL policy is working very well for the contingency constrained ACOPF as well. So for example, if we cut one of the lines and run this run our ADMM algorithm with the RL policy, is still running very well compared to the conventional parameter update scheme. So in conclusion, so we have developed the actually a first of its kind. I can say that our GPU solver is the first of its kind effort that can solve ACOPF problems fully on GPU without any data transfer between CPU and GPU. So we don't have any solution time deterioration because of the communication. And we also guarantee the algorithm convergence, and we have demonstrated the performance of the algorithm by using up to 70K. And all our project codes and other solvers. This is not only thing of our project. We have many different solvers available as well through this GitHub. And this project is ongoing project. Many colleagues are actively developing different ideas and algorithms and components. For example, we are actively working on multi-period ACOPF with energy storages. And there we have complementary constraint, which is difficult to tackle. And also on the side, we are working to tightly integrate the ML techniques, for example, to learn parameter update schemes. Yeah, and our key publications related to this talk is available here, archive. And thanks for our colleagues, Youngdae, Alisa, Sihan, and Mihai, and Mojan from Argonne and Georgia Tech. And I would like to acknowledge the funding support from DOE. Thank you, and I'll be happy to take any questions from the audience.
Thank you very much for that presentation, Kibaek. I think it's very exciting work on ACOPF, which is like one of the hardest problem to solve. So I'll again request the attendees to post their questions on the meeting chat, or you can unmute yourself and ask any questions that you have. So I can start with one question, Kibaek. I think the decomposition that you've done is you've kind of gone to the like the atom of or basically like the lowest level of decomposition that you can go to in terms of buses, generators. Usually the decompositions that I've seen in the literature tend to have subnetworks, which comprises of many generators, buses, and loads. So what prompted you guys to go down to that lowest level, like having each GPU thread tackle just one bus or one line or one generator? So
the main motivation was actually our frustration of using the linear algebra solver. As you know, I'm not the expert in linear algebra. And then what we did at the earlier stage of the project, we tried like linear servers and simply replacing these linear servers and tried to run on GPUs. And then we found that sparse linear algebra is not there yet for handling this type of problem. So then our motivation is that why don't we just decompose the problem into the smallest one that we can get? So that was our motivation.
Okay. Okay. Any other questions for Kibaek? Okay, so let me ask another question, Kibaek, and that is on the ADMM technique. Usually ADMM techniques do not have that much accuracy compared to just doing a linear circle. Can you comment a little bit about the accuracy of this method? And you also mentioned about global convergence, which is very exciting. So can you talk a little bit about the accuracy and the global convergence part again?
Yeah, that's a good question and comment. So yes, ADMM is basically limited by its nature, the first of the method. It's difficult to achieve high accuracy solution or greater convergence rate. So meaning that is if IPF or interior point type method would work in the end with the great sparse linear algebra GPU solver, then ADMM won't be able to beat them. So in theory, and this inaccurate solution is also limited by those factors, and partly because of the parameter tuning. So in the end, if we make more progress as we go along with this project, ADMM approach will be able to use as part of the initial step, and then maybe some other algorithm can be used to policy the solution accuracy if needed. Mm-hmm. Or some other techniques like post-processing can be used. So by fixing real power generations and voltage and solve power flow equations, and then we get a solution.
Right, right. And can you comment a little bit about the global convergence? There was a slide I saw that talked a little bit about global convergence.
So it was known to be really difficult to achieve the global convergence. So the global convergence meaning that the convergence of the algorithm really depends on the starting point. But having the global convergence means like whichever point we start the algorithm, we can achieve the convergence. So the algorithm will terminate with a local optimal solution. And this has been done by Andy Song and his students when Andy was in Georgia Tech. Yeah, it was exciting result.
Yeah, definitely. Okay, so one last call for any questions for Kibaek. Okay, if not, I will stop the recording here. Just wanted to again inform everyone that